The biggest galaxy we have ever discovered is so vast that the human mind struggles to truly comprehend it. This is not an exaggeration. And it is not a piece of dramatic storytelling. It is a quiet, measured truth about a cosmic giant that exists more than 1 billion light-years away from us. Suspended in the darkness, holding a number of stars that no human could ever count. Even across 1 million lifetimes. If you are anything like me, you may have believed you already understood what big means in space. You have seen how Jupiter dwarfs Earth. You have heard that our Sun could contain roughly 1 million Earths within its volume. You may have even imagined the scale of our own Milky Way galaxy, stretching across 100,000 light-years from edge to edge. But something subtle begins to shift the moment we step beyond those familiar comparisons. Because everything we have just described, every scale that once felt enormous, begins to lose its meaning when placed next to what astronomers have uncovered in a distant region of the universe. So for a moment, let the scale of everything you thought you understood begin to soften at the edges. Let the numbers drift slightly out of focus. Because what we are about to explore does not just expand your sense of size. It quietly rewrites it. Our home, the Milky Way, is what astronomers call a barred spiral galaxy. It is a vast structure with elegant, curving arms made of stars, gas, goddess, and dust, all slowly rotating around a dense central region where a supermassive black hole resides. From one edge to the other, this galaxy stretches across roughly 100,000 light-years. Even if you could travel at the speed of light, the fastest speed anything can reach in our universe, it would still take you 100,000 years to cross it. That scale alone is already difficult to truly absorb. 100,000 years is longer than the entire span of modern human history. It reaches back beyond written language, beyond cities, beyond the earliest traces of civilization. And yet, that immense distance is only the width of our own galaxy. Just one small region in a much larger universe. The Milky Way contains somewhere between 200 billion and 400 billion stars. Around many of those stars, there may be planets, and around those planets, moons, along with countless asteroids and comets drifting through the darkness. Our Sun is just one of these stars, located about 26,000 light-years from the galactic center, in a relatively quiet region known as the Orion Arm. Even here, nothing is truly still. Our entire solar system is moving, orbiting the center of the galaxy at a speed of about 500,000 miles per hour. And yet, despite that incredible velocity, it takes roughly 250 million years to complete a single orbit. Astronomers sometimes call this a galactic year. During the entire age of the dinosaurs, our solar system did not complete even one full circuit around the galaxy. The last time our Sun occupied roughly this position in its orbit, complex life on Earth had not yet emerged. The planet was dominated by simple organisms in the oceans. That is the timescale we are dealing with. And between the stars, there is almost nothing. The nearest star to us, a small red dwarf known as Proxima Centauri, lies about 4.2 light-years away. To make that distance more intuitive, imagine shrinking our Sun down to the size of a grain of sand. In that same scale, Proxima Centauri would be another grain of sand sitting several miles away. The space between them would be almost entirely empty, filled only with the faintest traces of gas, dust, and occasional high-energy particles drifting through the void. It is this emptiness, as much as the size, that makes our galaxy so difficult to truly comprehend. We live on a crowded planet, surrounded by billions of people and countless other forms of life. Everything around us feels close. dense, and full. But the moment you step beyond our solar system, that intuition begins to break down. In space, emptiness is not the exception. It is the rule. Stars are separated by such enormous distances that the chance of any two of them colliding by accident is effectively zero. In fact, entire galaxies can pass through one another, slowly drifting together and merging over time. And still, almost no stars actually collide. That is how vast the gaps are. And yet, even within that emptiness, there is enough material spread across thousands of light years to form hundreds of billions of stars in our galaxy alone. The gas and dust between stars may seem thin, but across those immense distances, it accumulates into staggering amounts of matter. Even now, new stars are being born inside giant molecular clouds scattered throughout the Milky Way. These are regions where gravity has pulled gas together until nuclear fusion ignites, lighting up new stars that will shine for millions or billions of years. Our galaxy is not static. It is alive, constantly changing. As new stars are formed while older ones fade and die, when you look up at the night sky from a truly dark place, that faint, glowing band stretching across the heavens is not a cloud. It is the combined light of billions upon billions of distant stars within our own galaxy. Ancient people saw that soft glow and imagined it as spilled milk across the sky, which is where the name Milky Way comes from. For most of human history, we believe that was everything. Different cultures created their own explanations for that band of light. The ancient Greeks spoke of milk spilled from the goddess Hera. The Romans called it the Milky Road. In India, it was seen as the path of souls. Aboriginal Australians imagined it as a river flowing across the sky, across time and place. People looked up at the same light and wondered what it meant. In the 17th century, when the first telescopes were turned toward the Milky Way, something remarkable happened. That soft glow resolved into countless individual stars, far too faint and too numerous to see with the naked eye. It was the first real hint that our galaxy was far larger than anyone had imagined. Then, in the 1920s, an astronomer named Edwin Hubble made a discovery that would change everything. Working at Mount Wilson Observatory in California, using what was then the largest telescope in the world, he studied a class of stars known as Cepheid variables. These stars pulse in brightness in a predictable way, allowing astronomers to measure their distance. Hubble used these stars to study what was then called the Andromeda Nebula, and what he found was extraordinary. It was not a cloud of gas inside our galaxy. It was an entirely separate galaxy, located far beyond the Milky Way. His early estimate placed it at about 1 million light-years away. Today, we know the true distance is closer to 2.5 million light-years. But the conclusion was unmistakable. The universe was far larger than we had ever imagined. Our galaxy was not the whole cosmos. It was just one among many, and not just a few. Today, we estimate there are around 2 trillion galaxies in the observable universe. 2 trillion, a number so large that it begins to lose meaning. A 2 followed by 12 zeros. Each galaxy containing billions or even trillions of stars. But here is where things become even more interesting. Not all galaxies are the same. Some are small dwarf galaxies, containing only a few billion stars. Others, like our Milky Way or the Andromeda Galaxy, are large spirals with structured arms and ongoing star formation. Then there are the true giants. Galaxies so massive that they make the Milky Way seem almost insignificant, like a single grain of dust floating in an enormous, empty hall. Galaxies come in many forms. Spiral galaxies, like our own. have flat rotating disks and graceful arms where new stars continue to form. Their structure is maintained by a balance between rotation and gravity. Elliptical galaxies are very different. They have no clear structure, ranging from nearly spherical to elongated shapes, and they are filled mostly with older red stars. Star formation in these galaxies has largely stopped, as they have used up most of their gas. The largest galaxies in the universe are almost always elliptical, formed through the gradual merging of many smaller galaxies over billions of years. There are also irregular galaxies, which have no defined shape at all. These are often distorted by gravitational interactions with nearby galaxies. The Magellanic Clouds, visible from the southern hemisphere, are examples of such galaxies, shaped in part by the gravity of the Milky Way. And galaxies themselves are not scattered randomly. They are organized into larger structures. Galaxy groups contain a handful to a few dozen galaxies, bound together by gravity, drifting slowly through the vast cosmic web. Our own Milky Way belongs to what astronomers call the local group, a collection of around 80 known galaxies, including Andromeda and dozens of smaller dwarf galaxies. Beyond this scale, galaxy clusters gather hundreds or even thousands of galaxies, all bound together by gravity. And beyond clusters, there are superclusters, immense structures stretching across hundreds of millions of light-years, forming some of the largest patterns in the observable universe. The galaxy I want to bring into focus now is one of these true cosmic giants. It carries a surprisingly simple name, Icomio Suta Unu, taken from its entry in a catalogue of celestial objects compiled more than a century ago. But behind that ordinary label lies something extraordinary. IC 1101 sits at the center of a massive galaxy cluster known as Abell 2029, located in the direction of the constellation Virgo as seen from Earth. When astronomers observe this region, they see a dense gathering of galaxies, all orbiting within a shared gravitational field. And at the very center of that structure, dominating everything around it, in this Eismil Fenton, like a silent anchor holding the entire system together, this galaxy is estimated to span somewhere between 4 million and 6 million light-years across. Let that settle in for a moment. Our Milky Way, which already feels unimaginably large, measures about 100,000 light-years in diameter. IC 1101 is roughly 40 to 60 times larger than that. If IC 1101 were placed where our Milky Way currently sits, it would not simply overlap with our galaxy, it would engulf our entire cosmic neighborhood. The Andromeda Galaxy, located about 2.5 million light-years away, would lie well within its vast structure. The Triangulum Galaxy would also be absorbed into its enormous reach. Even the many dwarf galaxies orbiting the Milky Way, including the large and small Magellanic Clouds, would become tiny, almost insignificant components within this colossal system. But size is only the beginning. IC 1101 is estimated to contain around 100 trillion stars. To put that into perspective, our Milky Way contains at most about 400 billion stars. That means IC 1101 holds roughly 250 times more stars than our home galaxy. Imagine trying to count them. One star every second, without ever stopping. It would take more than 3 million years just to reach 100 trillion. No pause, no sleep, no breaks, just counting, endlessly. The story of how we first noticed this galaxy goes back to the year 1790. A German-born British astronomer named William Herschel was surveying the night sky with his telescope, carefully cataloguing objects that had never been recorded before. On June 19th of that year, He pointed his instrument toward a region in the constellation Virgo and saw a faint, blurred patch of light. He noted its position and moved on. At the time, there was no way for him to know what he had found. The tools to measure such distances did not yet exist, and the idea that galaxies lay far beyond our own had not yet been established. To Herschel, it was simply another nebula, one of many mysterious objects scattered across the sky. For more than a century, that faint smudge remained just that, an entry in a growing list of unknowns. It was eventually labeled IC 1101 inches, what became known as the Index Catalogue, an extension of earlier astronomical records. But its true nature remained hidden. Everything changed in the 20th century. With more powerful telescopes and new methods for measuring cosmic distances, astronomers realized that IC 1101 was not part of the Milky Way at all. It was a separate galaxy, located more than 1 billion light-years away. The light we see from IC 1101 today began its journey toward us over 1 billion years ago. It has been traveling through space for that entire span of time, crossing the vast emptiness between galaxies before finally reaching our instruments. When that light first left IC 1101, life on Earth was still dominated by simple, single-celled organisms. Complex animals had not yet appeared. The age of dinosaurs was still hundreds of millions of years in the future. Every chapter of human history unfolded while that ancient light was still on its way. As astronomers studied IC 1101 more closely, they began to understand how it became so enormous. This galaxy did not grow through quiet, gradual processes alone. It expanded through repeated acts of cosmic merger over billions of years. IC 1101 is what scientists describe as a cannibal galaxy. It has grown by absorbing other galaxies. Within galaxy clusters, gravity pulls galaxies together. They move, interact, and sometimes collide. Over time, smaller galaxies are torn apart and gradually merged into larger ones. And at the center of a dense cluster like Abell 2029, a galaxy like IC 1101 has had billions of years to feed, slowly accumulating mass, growing larger and larger, until it became one of the most massive galaxies we have ever observed. And even now, that process may not be over. When two galaxies drift close to one another, their gravity begins to reshape them. Stars are pulled from their orbits. Gas and dust are stretched and compressed. And over time, the structures we recognize start to dissolve. If the galaxies are similar in size, they may slowly merge across hundreds of millions of years, becoming a single, larger system. But when one galaxy is far more massive, the outcome is different. The larger one absorbs the smaller, stripping away its stars and gas, quietly adding that material to itself. This is the long story of IC 1101. For billions of years, it has sat at the gravitational center of its cluster, drawing in smaller galaxies that wander too close. They spiral inward, gradually torn apart, their stars redistributed into the growing body of this giant. With each encounter, IC 1101 becomes a little larger, a little heavier, a little more dominant. Astronomers estimate that it has experienced at least 76 major mergers over its lifetime. And beyond those, countless smaller galaxies have also been consumed, barely noticeable against its immense scale. The evidence of this history is written directly into the galaxy's shape. Spiral galaxies like our Milky Way display elegant arms, regions rich with gas and active star formation. IC 1101 shows none of that structure. It is an elliptical galaxy, smooth and rounded, with no visible arms. This tells us that its past has been shaped by repeated mergers. Each collision disrupted any original structure, mixing the stars into a more random, evenly distributed form, like matter slowly stirred into a vast cosmic field. And yet, despite containing around 100 trillion stars, IC 1101 is no longer a place of creation. It is, in many ways, a dying galaxy. Most of its stars are old, many of them red giants or aging yellow stars that have already burned through much of their fuel. Very few new stars are being formed. The reason lies in how it grew. Every galaxy it absorbed brought not only stars, but also gas, the essential ingredient for star formation. Over time, that gas was either used up, heated, or expelled. Without cold gas, new stars cannot form. What remains is a quiet, aging system, still luminous, still immense, but slowly fading. The stars that exist will continue to shine for billions of years. But when they eventually burn out, there will be little left to replace them. IC 1101 is like an ancient empire that has expanded across everything around it, only to find itself without a future generation. At the very center of this galaxy lies something even more extreme. Like most large galaxies, IC 1101 hosts a supermassive black hole at its core. In our own Milky Way, the central black hole, Sagittarius A star, has a mass of about 4 million suns. In the Andromeda galaxy, the central black hole is larger, estimated between 100 million and 200 million times the mass of our Sun. But the black hole inside IC 1101 exists on an entirely different scale. Its mass is estimated to lie somewhere between 40 billion and 100 billion times that of the Sun. A single object, holding tens of billions of solar masses, compressed into a region from which nothing can escape. To give that some context, our Sun itself is already about 330,000 times more massive than Earth. Now imagine multiplying that solar mass by tens of billions. That is the scale of the object sitting silently at the center of IC 1101. The boundary around a black hole, known as the event horizon, marks the point beyond which escape is no longer possible. Not even for light. For a black hole of this size, the event horizon would extend to a radius of roughly 150 billion kilometers. That is an almost unimaginable distance. Our entire solar system, from the Sun out to the orbit of Neptune, spans about 9 billion kilometers. This means the event horizon of the black hole in IC 1101 is more than 10 times larger than our entire solar system. And everything within that boundary is forever cut off from the rest of the universe. A vast is a silent region defined only by gravity, holding within it one of the most extreme objects we have ever discovered. If we place this black hole at the center of our own solar system, where the Sun now sits, its event horizon would extend far beyond the orbit of Pluto, swallowing everything we consider home. The planets, the asteroid belt, the distant icy bodies, all of it would lie inside a region where escape is no longer possible. Near such an object, the laws of physics begin to feel unfamiliar. Time itself behaves differently. For someone falling toward the black hole, the outside universe would appear to speed up, events unfolding faster and faster. But to an observer watching from far away, that same person would seem to slow down. fading and freezing as they approach the edge. From the outside, they would never quite be seen crossing that boundary. Inside the event horizon, the structure of reality changes. All possible paths lead inward, toward the singularity at the center, a region where density becomes extreme and our current understanding of physics begins to break down. Anything that falls in would be stretched into long, thin strands by tidal forces, a process often described as spaghettification, where space itself pulls objects apart. And yet, despite its immense size and extreme nature, the black hole at the center of IC 1101 is not currently very active. It is not surrounded by a bright accretion disk, and it is not consuming large amounts of matter. It is, in a sense, quiet. Much of the easily available gas in the galaxy has already been used or expelled. Without a steady flow of material falling inward, the black hole has little to feed on. Occasionally, a star may wander too close and be torn apart, creating a brief flare of activity. But such events are rare. The black hole remains, vast and powerful, but largely dormant, mirroring the quiet state of the galaxy that surrounds it. There are still traces of its more active past. Astronomers have detected a radio source at the center of IC 1101, evidence of relativistic jets. Streams of particles accelerated to near the speed of light and launched outward from the region around the black hole. These jets are driven by rotation and magnetic fields, and over time, they carve enormous cavities in the surrounding gas. X-ray observations reveal these cavities as vast bubbles, regions where hot gas has been pushed outward by energy released near the black hole. Some of these structures extend across millions of light years, silent records of periods when the black hole was far more active than it is today. The energy involved in creating such features is extraordinary, comparable to the total output of billions of stars over millions of years. This interaction between black holes and their host galaxies is one of the most important areas of modern astrophysics. It suggests that supermassive black holes do not simply sit at the centers of galaxies. They help shape them. When gas begins to fall toward the center of a galaxy, the black hole can release enough energy to heat and expel that gas, preventing it from cooling and forming new stars. In this way, the black hole acts like a kind of regulator, influencing how the galaxy evolves over time. In EC 1101, this process may have played a key role in shutting down star formation. The galaxy and its central black hole have reached a kind of balance, each shaping the other across billions of years. Black holes grow by consuming matter, and when galaxies merge, their central black holes eventually do as well. Over the long history of IC 1101, repeated mergers have fed its central black hole again and again. Each incoming galaxy brought not only stars, but also another black hole, adding to the mass of the one at the center. The merging of supermassive black holes is a slow but powerful process. At first, they orbit far apart, surrounded by stars. Over time, gravitational interactions cause them to spiral closer together. Eventually, they form a binary system, circling each other as they lose energy. That energy is carried away in the form of gravitational waves, ripples in space-time itself. As these waves radiate outward, the orbit shrinks, and the black holes draw closer until they finally merge in an event of immense power. Such mergers release more energy than all the stars in a typical galaxy combined, though most of that energy is not in light, but in gravitational waves. These waves travel outward at the speed of light, stretching and compressing space as they pass. Only recently have we learned how to detect them. The first confirmed detection came in the mid-2010s. When observatories on Earth measured the signal from two smaller black holes merging more than 1 billion light-years away. Since then, many such events have been observed, opening an entirely new way of studying the universe. In the future, space-based detectors will be able to observe mergers of supermassive black holes like those that helped build the one in IC 1101. We will not just see the universe. We will, in a sense, begin to listen to it. Across billions of years, IC 1101's central black hole has grown through many such events. Each merger added mass, altered its rotation, and reshaped the surrounding galaxy. The gravitational interactions during these processes can even fling stars outward, leaving behind a core that is unusually large but less dense than expected. For a black hole with tens of billions of solar masses, the event horizon extends to roughly 150 billion kilometers, a region larger than our entire solar system. And within that boundary lies one of the most extreme environments we can imagine. Even now, faint radio emissions continue to emerge from the galaxy's center, a reminder that the black hole is not entirely silent. From time to time, it awakens briefly, releasing bursts of energy into the surrounding space. All of this raises a deeper question. The mass of a galaxy and the mass of its central black hole appear to be closely linked. Larger galaxies tend to host larger black holes. But which came first? Did the black hole grow and shape the galaxy around it? Or did the galaxy form first and build the black hole over time? The answer, as far as we can tell, is that they evolved together. Each influenced the other, growing in tandem across cosmic time. In IC 1100, this partnership reached an extreme. A galaxy that consumed countless others, and a black hole that grew alongside it, together forming one of the largest and most powerful systems we have ever observed. At the very center of this system lies a core stretching across nearly 14,000 light-years. A vast, diffuse region shaped by the repeated mergers of both galaxies and black holes over billions of years. That means the central core of IC 1101, not the entire galaxy, but just its innermost region, is already larger than most dwarf galaxies. This core alone contains more stars than entire galaxies scattered across the universe. And that is where the scale begins to slip beyond anything familiar. Now imagine, for a moment, that you could travel from one edge of IC 1101 to the other. You would need to cross somewhere between 4 million and 6 million light-years. Light itself, moving at about 6 trillion miles per year, would take millions of years to make that journey. And light is the fastest thing we know. So let us bring that down to something closer to human experience. The Voyager 1 spacecraft, launched in 1977, is the fastest object humanity has ever sent into interstellar space. It is moving at roughly 38,000 miles per hour relative to the Sun. At that speed, it would take about 80,000 years just to reach the nearest star, Proxima Centauri, which is a little over 4 light-years away. To cross the Milky Way at that same speed would take around 2 billion years. And to cross IC 1101, the journey would stretch between 80 billion and 120 billion years. That is longer than the current age of the universe itself. Even with our fastest technology, crossing a single galaxy like this is not just difficult, it is effectively impossible. Here is another way to picture it. If you were to shrink the Milky Way down to the size of a dinner plate, roughly 10 inches across, then IC 1101 would expand to something closer to the size of a large swimming pool. Everything we know, every star in our galaxy, every planet, every possibility of life within it, would be contained in something that small compared to this vast structure. And the light we see from IC 1101 today has been traveling for over 1 billion years to reach us. Every second, light leaves that galaxy and moves outward at about 186,000 miles per second. Over the span of 1 billion years, those photons have crossed 1 billion light-years of space before finally arriving here, carrying with them a snapshot of the past. When that light began its journey, life on Earth was still in its early stages of complexity. Our understanding of IC 1101 would not exist without advances in telescope technology. Early telescopes were limited by their size and by the distortions of Earth's atmosphere, which blurs and distorts incoming light. For much of the 20th century, astronomers could see that IC 1101 was large, but they could not resolve its structure in detail. That changed with the launch of the Hubble Space Telescope in 1990. Orbiting above the atmosphere, Hubble was able to capture sharp, detailed images of distant galaxies. Over time, it revealed the structure of IC 1101. Its enormous core, its extended halo of stars, and its position within a massive galaxy cluster. Since then, other telescopes observing at different wavelengths have added more pieces to the picture. Radio telescopes have detected emissions from the galaxy's central black hole. X-ray observatories have mapped the hot gas filling the surrounding cluster. Infrared instruments have allowed us to peer through dust and study the populations of stars within the galaxy itself. And yet, even now, there are limits to what we know. The exact number of stars in IC 1101 is still uncertain. Counting individual stars at such distances is extraordinarily difficult. The size of the galaxy depends on how we define its boundary. Because galaxies do not end abruptly, they fade gradually into intergalactic space. Even the mass of its central black hole can only be estimated within a range. What we do understand is that IC 1101 sits near the upper edge of how large galaxies can become. There may be slightly larger systems still waiting to be discovered. In recent years, astronomers identified a structure known as Alcyoneus, with radio lobes extending across about 16 million light-years. But that immense size comes from jets of energetic particles, not from the main body of stars and matter. When it comes to the actual structure of a galaxy, the stars, gas, and dark matter that define its physical form, IC 1101 remains one of the largest ever observed. It stands at the extreme end of the cosmic scale, a true giant among giants. And its story reveals something deeper about the universe itself. Galaxies do not appear fully formed. They grow over time. Small systems form first from collapsing clouds of primordial gas. Those systems merge, forming larger galaxies. Those larger galaxies merge again, building even more massive structures. This process, known as hierarchical structure formation, is one of the fundamental ideas in modern cosmology. The universe builds complexity slowly, step by step, through countless mergers across billions of years. IC 1101 is simply the most extreme example of that process we have found so far. It has had the time, the environment, and the opportunity to grow, quietly and relentlessly, into something that stretches the limits of what we thought was possible. But even something as vast as IC 1101 cannot keep growing forever. It has already consumed most of the galaxies that were close enough to fall into its grasp. The ones that remain are either too distant or moving too quickly to be captured. And slowly, almost imperceptibly, the expansion of the universe is carrying those remaining galaxies farther away, beyond its reach. At the same time, the universe itself is changing. Space is not just expanding, it is accelerating as it expands. This acceleration is driven by something we call dark energy, a mysterious component that makes up roughly 68% of the total energy in the universe, and yet remains one of the greatest unknowns in modern science. For much of the 20th century, astronomers believed that the expansion of the universe should be slowing down. Gravity, after all, pulls matter together. It seemed natural to assume that the combined gravitational pull of all matter would gradually slow the expansion that began with the Big Bang. But in the late 1990s, two independent teams studying distant supernova explosions made a discovery that changed everything. By using these supernovae as cosmic distance markers, they found that distant galaxies were not slowing down. They were moving away faster, and the expansion itself was accelerating. At first, the results seemed almost too strange to be true. But as more data was collected, the pattern became undeniable. Something was pushing the universe apart, overcoming gravity on the largest scales. That something was given the name dark energy. We still do not know what dark energy truly is. It may be a property of space itself, what Einstein once described as the cosmological constant. It may be a new kind of energy field that fills the universe, or it may be a sign that our understanding of gravity is incomplete. But whatever its nature, its influence is profound. As the universe continues to expand, galaxies grow more distant from one another, and there comes a point where the expansion of space carries them away faster than light can bridge the gap. When that happens, their light can no longer reach us. They slip beyond a kind of cosmic horizon and disappear from view. For IC 1101, this has a quiet but inevitable consequence. Its era of growth is coming to an end. There will come a time when there are simply no more galaxies left within reach to consume. It will become increasingly isolated, a vast and ancient structure drifting in a universe that is slowly emptying. Now, imagine the distant future from the perspective of that galaxy. IC 1101 sits at the center of the Abell 2029 cluster, surrounded by hundreds of galaxies bound together by gravity. For now, that gravitational bond is strong enough to resist the outward pull of cosmic expansion. But as time stretches forward, tens of billions of years into the future, even the broader universe will begin to fade. Distant galaxy clusters will vanish one by one, their light no longer able to cross the ever-expanding space between them. The observable universe, which today contains around 2 trillion galaxies, will begin to shrink from view. Within the cluster itself, things will continue for a while longer. The galaxies there are close enough to remain bound together. They will keep interacting, merging, and evolving. IC 1101 may still grow slightly, absorbing a few more neighboring systems. But eventually, even those galaxies will be drawn inward. Over immense stretches of time, perhaps hundreds of billions of years, the entire cluster may merge into a single, even larger galaxy. A final, colossal structure formed from everything that once surrounded it. And beyond that, there will be nothing visible. No distant galaxies. No clusters. No faint background of cosmic light. Only the stars of that merged system, shining in isolation against an endless darkness. A universe that has not ended, but has simply drifted out of reach. This is the isolation that awaits IC 1101. And in time, every structure in the universe, each one slowly cut off from the rest by the quiet, relentless expansion of space. Every galaxy becomes an island, alone with its own stars, its own history, drifting deeper into separation as the ages pass. And yet, even that isolation is not the final chapter. What happens to a galaxy when the universe itself begins to wind down toward what physicists call heat death is a story both immense and deeply quiet. Over the next 100 trillion years, the stars within IC 1101 will begin to fade. The most massive stars, the bright blue giants, disappeared long ago, burning through their fuel in only a few million years before ending in supernova explosions or collapsing into black holes. What remains today are longer-lived stars, slower, steadier, but still bound by time. Stars similar to our Sun live for about 10 billion years. Our own Sun is roughly halfway through that journey, with about 5 billion years remaining before it expands into a red giant, sheds its outer layers, and settles into a white dwarf. In EC 1101, countless stars have already followed that path, leaving behind faint, cooling remnants. Others are still shining, but their time will also come. The most enduring stars are the smallest ones, the red dwarfs. These tiny stars burn their fuel so slowly that they can shine for trillions of years. In a galaxy containing 100 trillion stars, there are unimaginable numbers of these faint, persistent lights. Long after larger stars have faded, red dwarfs will continue to glow, quietly extending the era of starlight. But even they are not eternal. The smallest red dwarfs, with only a fraction of the Sun's mass, may last up to 10 trillion years, hundreds of times longer than the current age of the universe. Yet eventually, even they will exhaust their hydrogen and fall dark. By around 100 trillion years into the future, star formation across the universe will effectively cease. The gas and dust required to form new stars will have been used up or dispersed too thinly to collapse under gravity. No new light will be born to replace what is lost. One by one, the stars of IC 1101 will fade. The galaxy will dim gradually, almost imperceptibly, over spans of time so vast they make the present age of the universe feel like a brief moment. What was once a brilliant collection of stars will become a quiet assembly of remnants. White dwarfs, neutron stars, black holes. These will drift through the expanding darkness, still bound within the remains of what was once a galaxy of extraordinary scale. IC 1101 will persist, but only as a shadow of its former self, a structure no longer defined by light, but by the memory of it. And still, even this is not the end. Over timescales so vast they stretch beyond ordinary language, even these remnants will continue to change. White dwarfs will cool, slowly radiating away their remaining heat until they become black dwarfs. Objects so cold they emit no light at all. This transformation takes on the order of 10 to the 15th power years, a span so immense it is difficult to truly hold in thought. By then, the universe will have entered a state of deep, enduring darkness. Not empty, but quiet. Not gone, but transformed into something far colder, far slower, and far more distant than anything we experience today. That is roughly 100,000 times longer than the current age of the universe. A scale so extreme that it forces us to rethink what we mean by long term. And yet, even on those timescales, the story is still unfolding. Neutron stars, those ultra-dense remnants of stellar collapse, may not be permanent either. Their fate depends on something we still do not fully understand. Whether protons, the building blocks of matter itself, are truly stable, or whether they eventually decay. Some models in particle physics suggest that protons may decay over timescales around 10 to the 34th years or longer. If that turns out to be correct, then even the most stable matter in the universe is only temporary. The atoms inside neutron stars, white dwarfs, planets, and every structure we have ever observed would slowly break down, dissolving into a thin bath of radiation spread across space. But before we reach that stage, another process quietly takes over, one that reshapes even the most extreme objects in the cosmos. Black holes, including the enormous one anchoring IC 1101, are not eternal. Through a mechanism known as Hawking radiation, they slowly lose mass over time. This idea, first proposed by Stephen Hawking, reveals that black holes are not perfectly black, but instead emit a faint trickle of particles due to quantum effects near the event horizon. At that boundary, pairs of particles continuously appear and vanish. Occasionally, one falls inward while the other escapes, carrying away a tiny amount of energy. It is an almost imperceptible process. But given enough time, it adds up. The black hole shrinks, slowly and steadily, over durations that stretch far beyond the era of stars. For a black hole with the mass of our Sun, the evaporation time is around 10 to the 67th years. But the central black hole of IC 1101 is vastly larger, containing tens of billions of solar masses. That pushes the timescale to something on the order of 10 to the 100th years. A number so large that writing it out fully becomes almost meaningless in practical terms. And here is where perspective shifts again. Compared to these durations, everything we have discussed so far, from the formation of galaxies to the death of the last stars, becomes almost negligible. The entire luminous history of the universe compresses into a tiny fraction of what comes next. But even this is not the end of the story. Eventually, after incomprehensibly long stretches of time, even these supermassive black holes will fade. The process is slow, but it is relentless. The mass decreases, the radiation increases, and at the very end, the black hole releases its final energy back into the universe. What follows is not an explosion in the dramatic sense, but a final transition. The last concentrated structures dissolve, leaving behind only diffuse particles and radiation. No stars, no galaxies, no compact remnants. Just a thin, expanding background of energy spread across an ever larger volume of space. And that raises a deeper question, one that we will explore as we continue. If even the most massive and long-lived structures cannot survive indefinitely, what does that tell us about the ultimate structure of the universe itself? What remains when every process that creates order has run its course? What we see when we look at IC 1101 is the largest scale on which the universe has gathered matter into something structured and coherent. A record written not in words but in stars, in motion, in gravity acting over billions of years. It is the result of countless mergers, collisions, and interactions. A history shaped by forces that are often violent, yet capable of producing something unexpectedly ordered and vast. It is easy to call it a monster, but it is also a kind of monument. A monument to the laws of physics that have been at work since the first atoms formed, slowly building complexity from simplicity, structure from chaos, across stretches of time that are almost impossible to fully imagine. Now bring that perspective closer to home. The same processes that shaped IC 1101 are not distant or abstract. They are happening here, within our own galaxy. Even now, the Milky Way is not isolated or static. It is part of the same ongoing cosmic evolution, quietly interacting with its surroundings. At this very moment, Our galaxy is in the process of absorbing smaller companions. The Canis Major dwarf galaxy is being torn apart and drawn inward. The Sagittarius dwarf galaxy is stretched into long streams of stars that wrap around the Milky Way, leaving behind faint trails that we can still observe, like echoes of structures that once existed on their own. And this is only the beginning. Looking ahead, there is the possibility of a much larger encounter. The Andromeda Galaxy, our nearest large neighbor, is moving through space in our direction. For decades, scientists believed that a collision between the Milky Way and Andromeda was almost certain, expected to occur in roughly 4 to 5 billion years. More recent data has introduced some uncertainty into that picture. Observations from the Gaia spacecraft and the Hubble Space Telescope suggest that when we include the gravitational influence of nearby galaxies such as the Large Magellanic Cloud and Triangulum, the outcome becomes less predictable. Some models now estimate only about a 50% chance that the two galaxies will actually merge within the next 10 billion years. But whether the merger happens sooner, later, or not at all, the underlying principle remains the same. Galaxies are not permanent structures. They evolve, interact, and sometimes combine. This is not an exception in the universe. It is the rule. If such a merger does occur, it would unfold over billions of years. Not as a sudden collision, but as a gradual and complex interaction. Stars would pass by one another with vast distances between them, rarely, if ever, colliding directly. But the gravitational effects would reshape both galaxies completely. The elegant spiral arms of the Milky Way and Andromeda would be disrupted and eventually erased. Clouds of gas would compress, triggering waves of new star formation. At the centers, the two supermassive black holes would spiral toward each other and eventually merge, releasing powerful gravitational waves that ripple outward through space. Over time, the chaos would settle. What was once two distinct spiral galaxies would become a single, larger elliptical galaxy. Smoother, less structured, more like IC 1101 inches form, though far smaller in scale. To any distant observers in that far future, it might appear calm and featureless, with no obvious trace of the dramatic history that created it. By then, Earth itself will no longer exist. In about 5 billion years, our Sun will expand into a red giant, growing large enough to engulf the inner planets. Whether life, intelligence, continues elsewhere is something we cannot yet know. And this is where IC 1101 gives us a different kind of perspective. It reminds us that the universe operates on timescales far beyond human experience, beyond civilizations, beyond even the lifetimes of planets. Yet at the same time, it shows us something else. We are able to see it. We are able to understand it, at least in part. A galaxy more than 1 billion light years away, containing around 100 trillion stars. And we have measured its size, traced its history, and inferred what lies at its center. That alone is extraordinary. And it leads to a question that stays with us as we continue exploring. If we can reach this far with our understanding, what else might still be waiting? Just beyond what we currently know. Human beings, living on a small rocky planet orbiting an ordinary star in a quiet corner of an average spiral galaxy, have somehow developed the ability to understand objects so distant that their light began its journey before complex life even existed on Earth. That ability is not trivial. In a universe governed by blind physical laws, by particles and energy moving without intention, something remarkable has happened here. Consciousness has emerged. Minds capable of asking questions, forming theories, testing ideas, and slowly building an understanding of reality. Whatever else we may be, we are the part of the universe that has become aware. The part that has started to look back at itself and wonder what it is and how it came to be. Now consider something equally profound. Iko mio sute uno. For all its unimaginable size, is made of the same fundamental ingredients as we are. The stars within it burn hydrogen into helium, just like our sun. The atoms in those stars, carbon, oxygen, nitrogen, iron, are the same elements that make up our bodies. They were forged in stellar furnaces, scattered by ancient explosions, and eventually became part of us. There is a continuity here, a deep connection that is easy to overlook. We are not separate from the universe. We are built from it. The same processes that assembled a galaxy of 100 trillion stars also assembled the molecules that think, feel, and reflect. The light from distant galaxies and the light in our own eyes are part of the same story. And then there is a third perspective to consider. The universe did not have to be structured in a way that allows any of this to happen. If the fundamental constants were even slightly different, gravity stronger, nuclear forces weaker, expansion faster, then stars might never have formed. Galaxies might never have existed. The universe could have remained a thin, featureless sea of particles, or collapsed back into itself shortly after it began. Instead, we find ourselves in a universe where structure is possible, where matter can gather, ignite, evolve, and organize into systems of increasing complexity. IC 1101 stands as an extreme example of what those simple laws, given enough time, can produce, not by design, not by intention, but through the steady, cumulative effects of physics acting over billions of years. And that naturally leads to a larger question. If the universe is capable of creating something like IC 1101, what else might exist beyond what we have already discovered? What other structures? What other phenomena? What other levels of complexity are still waiting? Just beyond the edge of our current observations, every step in our understanding has followed this same pattern. We once believed Earth was at the center of everything. Then we learned we orbit the Sun. Then we realized the Sun is just one star among hundreds of billions. Then we discovered that our galaxy is only one among trillions. Each step has made our physical position seem smaller. But it has also revealed a universe that is far richer and more intricate than we previously imagined. IC 1101 is another step in that progression. It expands the scale of what we know to be possible. It challenges our assumptions and invites us to keep looking further, to keep refining our understanding, to keep asking questions that do not yet have answers. And in the face of that scale, there are two ways to respond. One is to focus on how small we are, how brief our lives are compared to cosmic time. The other is to recognize something equally important. We are the ones asking these questions. We are the ones uncovering these structures, measuring their light, reconstructing their histories. Now imagine, just for a moment, that you are drifting somewhere near the outer regions of IC 1101. In every direction, stars extend outward in vast numbers, not thousands or millions, but trillions. Each one a sun, each one a source of light that has been shining across immense stretches of time. There is no clear center from where you are. It is too far away, hidden behind layers upon layers of stars. There is no sharp edge either. The galaxy fades gradually into the darkness. blending into intergalactic space so smoothly that the boundary becomes almost impossible to define. You are surrounded by a structure so large that crossing it would take far longer than the entire history of human civilization. Longer than anything we intuitively understand as time. And yet, far away. More than 1 billion light-years from where you drift. There is a small planet orbiting an ordinary star. On that planet, beings exist who live for only a brief moment in cosmic terms. And still, they have discovered this place. They have measured its scale, studied its light, inferred the presence of the black hole at its center, and traced its evolution across billions of years. And that brings us to the next question. The one that naturally follows from all of this. If we can understand something this vast from so far away, what might be the limits of what we can eventually know? They have placed IC 1101 within the context of the entire universe and recognized its scale and significance. And perhaps the most remarkable part is not simply that such a galaxy exists, but that we have been able to discover it at all. But instead of stopping here, we can go deeper. Because understanding IC 1101 is not about memorizing numbers or records. It is about understanding the processes that shape everything in the cosmos, including the history of our own galaxy. To see that more clearly, we need to look inside a galactic merger. Because when we say IC 1101 has absorbed dozens of galaxies, it is easy to imagine something simple, almost like one object swallowing another. In reality, the process is far more complex and far more elegant. It begins long before the galaxies actually meet. Even when separated by millions of light-years, their gravitational fields begin to interact, gently distorting their shapes and altering the motion of stars and gas within them. As the galaxies draw closer, those distortions become more dramatic. Stars that once followed stable orbits begin to shift, pulled in new directions. Vast clouds of gas are stretched and redirected. If we could compress millions of years into a short moment, the galaxies would appear to stretch and warp, forming long, luminous streams of stars that extend far into space. These are tidal tails, enormous structures that can reach hundreds of thousands of light-years, tracing the gravitational struggle between the merging systems. The first encounter is rarely the final one. The galaxies pass through each other, then separate again, slowed but still moving. Yet they are no longer independent. Gravity binds them together, pulling them back for another pass. Over hundreds of millions of years, this repeated motion continues, each encounter bringing them closer, until eventually they merge into a single, unified system. During this process, something extraordinary happens within the gas of both galaxies. Gravitational compression and shock waves trigger intense bursts of star formation. Entire regions ignite with new stars, forming in numbers so large that the galaxy can temporarily become one of the brightest objects in its surroundings. These events, known as starbursts, represent brief but powerful phases of creation amid the overall destruction. At the same time, material is funneled toward the centers of the merging galaxies. Gas falls inward, feeding the supermassive black holes that reside there. As they consume this material, the black holes release enormous amounts of energy, sometimes shining as quasars visible across vast cosmic distances. For a time, the centers of these galaxies can outshine all the stars within them combined. Eventually, the turbulence begins to settle. The two galaxies lose their original identities and become one. The elegant spiral structures that may have once defined them are erased by the gravitational interactions. In their place remains a larger, smoother system, typically an elliptical galaxy, where stars move in more complex and less ordered paths. This is the path IC 1101 followed. Not once, but many times. Each merger added more stars, more mass, and more material to its central black hole. Each event reshaped its structure, gradually erasing any trace of its original form. Over billions of years, through repeated cycles of interaction and integration, it grew into the immense galaxy we observe today. We can still see traces of that history. When astronomers study the stars in IC 1101, they find distinct populations with different ages and chemical compositions. Some stars are ancient, remnants of the earliest stages of the galaxy. Others formed later, during bursts of star formation triggered by mergers. Still others carry chemical signatures that suggest they originated in entirely different galaxies, systems that were later absorbed and blended into IC 1101. Even the core of the galaxy reveals clues. It is vast, stretching nearly 14,000 light-years across. Yet it is unexpectedly faint for its size. This likely reflects a history of repeated mergers involving supermassive black holes. When two such black holes come together, they form a binary system, orbiting each other before eventually merging. During this process, they interact with nearby stars, accelerating many of them and ejecting them outward. This phenomenon, known as gravitational scouring, can clear out the central region of a galaxy, leaving it less densely populated than expected. In the case of IC 1101, this process has likely occurred multiple times, each merger removing more stars from the core. Over time, this has created a massive central region that appears underpopulated compared to theoretical models. Estimates suggest that an enormous amount of stellar material, possibly hundreds of billions of solar masses, has been displaced in this way. That is more mass than contained in many entire galaxies, redistributed or even ejected as a result of these interactions. What makes all of this especially remarkable is how we know it. We cannot travel to IC 1101. We cannot directly sample its stars or observe its history in real time. All we have is the light that reaches us. Photons that have traveled for over 1 billion years before being captured by our telescopes. Yet from that light, we can reconstruct an intricate history of formation, interaction, and transformation. We are, in a very real sense, reading the history of the universe written in light. And when we step back even further, IC 1101 becomes part of a much larger picture. It is not the only extreme object out there. The universe contains a wide range of galaxies, each shaped by different histories and environments. Understanding where IC 1101 fits within that broader landscape helps us see not just how large it is, but how the universe itself explores every possibility allowed by its laws. At one end of the cosmic scale, we find dwarf galaxies, the smallest galactic systems in the universe. Some contain only a few million stars, others a few billion. And the faintest among them, like Segue Uno, hold only around 1,000 stars. They are so dim that we only began discovering them in the 21st century with advanced sky surveys. And yet, despite their size, dwarf galaxies play a fundamental role. They are the building blocks of everything larger. In the early universe, most galaxies began as these small systems, gradually merging over billions of years to form the larger galaxies we see today. Even giants like the Milky Way and IC 1101 trace their origins back to countless dwarf galaxies coming together. Moving up in scale, we encounter systems like the Large Magellanic Cloud, a satellite of the Milky Way located about 160 0.000 light-years away. It contains roughly 30 billion stars and spans about 14,000 light-years across. From the southern hemisphere, it appears as a faint, cloud-like patch in the night sky. But what you are really seeing is an entire galaxy. And even now, it is slowly being pulled apart. Gas is stripped from it, its structure distorted. And over time, it will be fully absorbed into the Milky Way. Another example of galactic cannibalism happening quietly in our own cosmic neighborhood. Then there are galaxies like our own. Spiral galaxies typically contain between 100 billion and 400 billion stars and stretch across 100 billion. 000 to 200 light-years. They are among the most familiar structures in the universe. With their elegant spiral arms and ongoing star formation, our nearest large neighbor, the Andromeda Galaxy, is even bigger, holding perhaps 1 trillion stars and extending about 220,000 light-years across. Under dark skies, it appears as a faint smudge, but that faint glow is the combined light of an entire galaxy. The most distant object most people will ever see with the naked eye. Beyond these lie the true giants. Massive elliptical galaxies at the centers of galaxy clusters. These can contain several trillion stars and span hundreds of thousands of light-years. They are already among the largest known structures made of stars. And yet, even they fall short of IC 1101. IC 1101 sits at the extreme end of this hierarchy. With a diameter of roughly 4 to 6 million light-years, it is tens of times larger than Andromeda. Its estimated 100 trillion stars place it far beyond most galaxies in sheer scale. There are very few known systems that can even approach it in size when we are talking about the actual stellar body of a galaxy. There is, however, one category that can appear even larger: the giant radio galaxies. These systems produce enormous jets powered by their central black holes, extending millions of light-years into intergalactic space. The most extreme example known so far is Alcyoneus, discovered in 2022, with radio lobes stretching across about 16 million light-years. That makes it larger than IC 1101 inches total extent, but the distinction matters. Those Vishal structures are not filled with stars. They are mostly extremely diffuse plasma and magnetic fields. The galaxy itself, the part made of stars, is relatively ordinary compared to IC 1101. So when we ask what the biggest galaxy is, we have to be precise. If we mean the largest structure associated with a galaxy, then giant radio galaxies like Alcyoneus take that title. But if we mean the largest collection of stars, the most massive stellar system, then IC 1101 remains unmatched. There is another way to think about size as well. Not in terms of diameter, but total mass. And this is where things become even more interesting. Because most of a galaxy's mass is not visible at all. It is in something we call dark matter. Dark matter does not emit or absorb light. It does not interact with normal matter in any way we can directly detect, except through gravity. But its presence is undeniable. When astronomers measure how fast stars orbit in the outer regions of galaxies, they find that there is far more gravitational pull than visible matter can account for. The only explanation that fits the data is that galaxies are embedded in massive halos of unseen material. In galaxies like the Milky Way, dark matter makes up around 90% of the total mass. The stars, gas, and dust we can see are only a small fraction of what is really there. IC-1101 is no exception, but on a far larger scale. Its total mass, including dark matter, may reach around 100 trillion times the mass of the Sun, and its dark matter halo likely extends far beyond its visible stars, possibly stretching tens of millions of light-years into space. This means that even when we think we are looking at the largest galaxy ever discovered, we are only seeing a small part of the full structure. Most of what defines IC 1101 is invisible, detectable only through the way it shapes the motion of stars and the bending of light. And that leads to one of the biggest challenges in modern physics. We still do not know what dark matter actually is. It could be a new kind of particle that barely interacts with normal matter, passing through everything without leaving a trace. Experiments around the world are trying to detect it directly, but so far, it remains elusive. So even with something as immense as IC 1101, our understanding is incomplete. We can measure its light, map its structure, and reconstruct its history. But the majority of its mass is still hidden from us. There is still a deeper layer of reality that we have yet to uncover. And before we move further, it is worth pausing to consider something else. The only reason we can know any of this, the only reason IC 1101 is more than just a distant blur, is because of the tools we have built and the knowledge accumulated over centuries. The story of observing distant galaxies begins with the earliest telescopes. When Galileo first pointed his instrument toward the sky in the early 17th century, he revealed details of the Moon and the moons of Jupiter. But galaxies like IC 1101 were completely beyond reach. Their light was simply too faint. Over the next few centuries, telescopes grew larger and more powerful. Bigger mirrors collected more light, allowing astronomers to detect objects that were previously invisible. Step by step, generation by generation, our view of the universe expanded, and with it, our ability to reach further into the darkness and uncover structures like IC 1101. Better optics brought sharper images. But for a long time that was not enough. When William Herschel first observed IC 1101 inches the late 18th century, even with one of the largest telescopes of his time, all he could see was a faint, diffuse glow. There was no way to know that this dim patch of light was actually an immense galaxy far beyond our own. The real transformation in our understanding came much later. As new technologies began to extend the reach of human observation, photography was one of the first major breakthroughs. Instead of relying on the human eye, astronomers could now collect light over long exposures, sometimes lasting hours. This allowed faint objects to gradually emerge from the darkness, revealing structures that were previously invisible. Spectroscopy added another layer of insight by splitting light into its component wavelengths, allowing scientists to identify the elements present and measure how fast objects were moving through space. Radio astronomy opened an entirely new window. By detecting wavelengths far beyond visible light, astronomers could observe phenomena hidden from optical telescopes. In the case of IC 1101, radio observations revealed activity associated with its central black hole, including jets that would otherwise remain unseen. Each new method did not replace the previous ones, but added another dimension, slowly building a more complete picture. One of the most important steps forward came with space telescopes. Earth's atmosphere, while essential for life, limits what we can observe. It absorbs certain wavelengths and distorts incoming light, reducing clarity. By placing telescopes above the atmosphere, astronomers removed those limitations. The Hubble Space Telescope, launched in 1990, played a crucial role in studying distant galaxies. From its position in orbit, it captured images with a level of detail that ground-based instruments could not match at the time. Observations from Hubble allowed scientists to examine the structure of IC 1101 more precisely, including its unusually large and faint core. These measurements helped confirm models of how massive galaxies evolve through repeated mergers. Other space observatories contributed in different ways. X-ray telescopes revealed the hot gas surrounding the galaxy, while infrared instruments detected older stellar populations that dominate elliptical galaxies. At the same time, ground-based telescopes continued to improve. Techniques like adaptive optics made it possible to correct for atmospheric distortion in real time, producing images that approach the clarity of space-based observations. Modern telescopes with mirrors tens of meters across can gather enormous amounts of light, allowing astronomers to study extremely faint and distant objects in remarkable detail. New instruments are pushing these capabilities even further. The James Webb Space Telescope is already providing deeper views of the universe in infrared light, while the next generation of ground-based observatories will extend our reach even more. With each advancement, our ability to study galaxies like IC 1101 becomes more refined, revealing details that were once completely out of reach. But observing distant galaxies is only part of the challenge. We also need to know how far away they are. Distance is one of the most fundamental quantities in astronomy, yet it cannot be measured directly for remote objects. Instead, astronomers rely on a sequence of methods known as the cosmic distance ladder. For nearby stars, parallax provides a direct measurement. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant ones. By measuring that shift, astronomers can calculate distance with high precision. However, this method only works for relatively close objects. For greater distances, astronomers turn to standard candles, objects whose intrinsic brightness is known. One example is Cepheid variable stars, which pulsate in a predictable way that reveals their true luminosity. By comparing how bright they appear from Earth to how bright they actually are, distance can be determined. But even Cepheids are too faint to be seen in galaxies as distant as IC 1101. For truly vast distances, astronomers rely on brighter events, such as Type Ia supernovae. These stellar explosions reach nearly uniform peak brightness, making them reliable indicators of distance. Another key method involves measuring redshift, the stretching of light as the universe expands. The more distant an object is, the more its light is shifted toward longer wavelengths. By combining these techniques, astronomers have determined that IC 1101 lies roughly 1 billion light-years away. This means that when we observe it, we are not seeing it as it exists today, but as it was when that light first began its journey toward us. And that realization adds another layer to the story. 1 billion years ago, Earth was a very different world. Complex life had not yet taken hold. The planet was dominated by simple organisms, and the long path toward intelligence had barely begun. Yet even then, light was leaving IC 1101, traveling across space, carrying with it information that would one day be captured and understood. And that leads to a quiet but powerful question. If every observation is a glimpse into the past, then what does that mean for how we understand the universe as it exists right now? 1 billion years ago, Earth itself would have been almost unrecognizable. The continents were arranged differently. The atmosphere had a different composition, and complex life had yet to emerge. While all of that slow transformation unfolded here, light from IC 1101 was already on its way, crossing the vast emptiness between galaxies, traveling through intergalactic space, occasionally bending under gravity, but never stopping. It moved at the fastest speed possible. And still, The journey took over 1 billion years. What we see through our telescopes today is not IC 1101 as it is now, but as it was in that distant past. Over that immense span of time, the galaxy could have changed in countless ways. Stars may have faded. New ones may have formed. And entire smaller galaxies may have already been absorbed into its structure. The central black hole may have gone through cycles of intense activity or long quiet periods. But whatever IC 1101 looks like today, that information has not reached us yet. In that sense, astronomy is a form of cosmic archaeology. Every observation is a look into the past. The farther away we look, the further back in time we see. This is both a limitation and a powerful advantage. We cannot observe the present state of distant objects, but we can reconstruct history by observing galaxies at different distances, each representing a different moment in cosmic time. By comparing these snapshots, astronomers can trace how galaxies evolve. Icomio suta unu, as we see it, is one frame in that long story. A giant galaxy captured at a specific stage of its development. Other galaxies, closer or farther away, fill in the rest of the timeline, allowing us to piece together how such enormous systems form and change over billions of years. But there is another challenge, one that is more subtle. The numbers involved are so large that they become abstract. 100 trillion stars, millions of light years, billions of years. These are not scales the human brain is designed to intuitively understand. We evolved to measure distances we can walk, time spans we can live through, quantities we can count. Cosmic scales exist far beyond that framework, so we try to translate them into something more tangible. Imagine taking a photograph of every star in IC 1101, one image per second, without ever stopping. It would take more than 3 million years to capture them all. If you had started when the earliest humans appeared, you would still be far from finished today. Or consider the grains of sand on every beach on Earth. Estimates suggest there are hundreds of trillions of grains. IC 1101 contains roughly that many stars. Each one is a sun, a source of energy, potentially surrounded by planets, each with its own story unfolding in silence. Now imagine crossing that galaxy, walking continuously at a steady human pace, never resting. It would take tens of trillions of years to go from one side to the other. That is thousands of times longer than the entire age of the universe so far. Even light itself, moving at its ultimate speed, would need millions of years to travel across it. Communication from one edge to the other would unfold over geological timescales, not human ones. These comparisons do not make the scale fully comprehensible, but they begin to anchor it in something we can feel, if not fully grasp. And that naturally leads to a question many people wonder about. In a galaxy with 100 trillion stars, could there be life? Even intelligent life? Science does not yet have a direct answer. We do not currently have the ability to detect life in galaxies that distant. Even within our own solar system, the search is still ongoing. But we can consider probabilities. If planets form around stars, and if even a small fraction of those planets can support life, then a galaxy with vastly more stars offers vastly more opportunities. The Milky Way may contain hundreds of billions of planets. Even if only a tiny fraction host life, that could still mean millions of living worlds. Scaling that idea up to IC 1101, with its enormous population of stars, suggests the possibility of an immense number of planets. Even under very conservative assumptions, there could be vast numbers of worlds where life has emerged, and perhaps some where intelligence has developed. But these remain possibilities. not observations. We do not yet know how common life is, or how often intelligence arises, or how long it persists. And even if such civilizations exist within IC 1101, the distances involved would make any form of contact extraordinarily unlikely. And that brings us to the deeper layer of the question, one that is less about numbers and more about perspective. If the universe is filled with possibilities on such a scale, what does that mean for how we understand our own place within it? We still do not know how common life truly is in the universe. We do not know how often simple chemistry becomes biology, or how often biology becomes intelligence. We do not even know whether life must resemble what we understand on Earth. Perhaps it does not require oceans. Perhaps it does not depend on carbon. Perhaps it unfolds in forms we have not yet imagined. But what we can say is this. IC 1101 offers an enormous canvas for whatever processes might give rise to life. For billions of years, this galaxy has been forming stars. Inside those stars, heavier elements were forged: carbon, oxygen, iron, and scattered across space through countless supernova explosions. The ingredients for complexity have been mixed and remixed over timescales almost impossible to comprehend. Whatever the recipe for life might be, IC 1101 has had both the time and the raw materials to attempt it. And if somewhere within that vast galaxy, intelligence has emerged, then their view of the universe would be very different from ours. Here on Earth, our night sky is mostly dark. A scattering of stars and the faint band of the Milky Way stretching across the horizon. But in a giant elliptical galaxy like IC 1101, the sky would not feel empty. It would feel crowded. Near the center, stars are packed far more densely than in the disk of a spiral galaxy like ours. The night sky there might not be dark at all. It would glow. Billions of nearby stars, so close together that true darkness might never fully exist. A kind of permanent twilight, where the sky itself becomes a continuous field of light. In such a place, constellations would lose meaning. Navigation by stars would become nearly impossible, not because there are too few, but because there are too many to distinguish. Further away from the center, the sky would calm, but it would still be unfamiliar. There would be no spiral arms tracing patterns across the heavens, no bright band marking the plane of a galactic disk. Instead, stars would surround the observer in every direction, distributed in a more spherical pattern, a shell of light enclosing the sky. And somewhere within that environment, on one of hundreds of trillions of possible worlds, there could be observers. Observers looking up and asking questions. Would they understand the history of their galaxy? Would they know that their home was built through billions of years of mergers, the remnants of smaller galaxies consumed over time? Would they have discovered the enormous black hole at their center? Would they have measured the age of their universe, as we have tried to do here on Earth? We cannot know, but it is difficult not to imagine that somewhere in IC 1101, there may be minds asking the same questions we ask. Looking out into the distance, seeing other galaxy clusters as faint smudges of light, and wondering if those distant structures contain other forms of intelligence. They might even see the Milky Way. From their perspective, it would not stand out. Just another spiral galaxy, one among billions. And that realization carries a quiet implication. The universe is not only vast in size, it is vast in possibility. Every galaxy becomes a potential experiment. Every cluster, a larger system shaping what those galaxies become. And IC 1101 is not isolated. It sits at the center of a massive structure known as the Abell 2029 galaxy cluster. A gravitational system containing hundreds of galaxies, all bound together, all moving within the same enormous well of gravity. Understanding this cluster is essential to understanding why IC 1101 became so large in the first place. Because galaxies do not grow alone, they grow within environments. In clusters like Abell 2029, the space between galaxies is not empty. It is filled with extremely hot gas, heated to tens of millions of degrees by the gravitational energy released as the cluster formed. This cluster is what astronomers call relaxed. Not in the sense of being inactive, but in the sense that it has had billions of years to settle into a stable configuration. Over time, something interesting happens. The most massive galaxies begin to sink toward the center. Not instantly, but slowly, through a process known as dynamical friction. As large galaxies move through a sea of smaller ones, they experience a kind of gravitational drag, losing energy, spiraling inward. And at the very center of this process, IC 1101 waits. At the deepest point of the gravitational well, where galaxies are most densely packed. This is not a coincidence. It is the reason IC 1101 became what it is. As other galaxies drifted inward, they encountered it. And over time, they were absorbed, one by one, across billions of years. The same process that pulled IC 1101 to the center also fed it, turning it into a cosmic collector of galaxies. But this is only part of the story. Because the environment around IC 1101 is not just made of galaxies, it is also filled with something far more subtle, a vast, nearly invisible ocean of hot gas, and that gas may hold the key to what happens next. Over the next several billion years, that early galaxy did not remain alone. It grew, slowly at first, then relentlessly. Merger after merger unfolded across cosmic time. Each time a smaller galaxy drifted too close, gravity would take hold, pulling it inward, stretching it, and eventually absorbing it. With every merger, new stars were added, new gas was delivered, and at the center, the black hole grew, feeding quietly on the incoming matter. The galaxy expanded, not in a sudden burst, but through a long, patient accumulation. And because it sat in a dense region of the universe, there was always more to consume. By around 10 billion years ago, this ancestor had already become something extraordinary. A giant elliptical galaxy forged through dozens of major mergers. Even then, it would have stood out, one of the largest structures in its region of space. But it was not finished yet. The universe itself was changing. Star formation across the cosmos began to slow. Galaxies were using up their gas. And as space expanded, the distances between galaxies increased, making encounters less frequent. The era of rapid growth was coming to an end. But IC 1101 was not in an ordinary place. It sat at the center of the Abell 2029 cluster, a region where gravity still pulled matter inward. Galaxies continued to fall toward the center, drawn by the combined mass of everything around them. And when they arrived, they encountered IC 1101. Even as the universe slowed down, this galaxy continued to grow. Dozens more major mergers, countless smaller ones, each interaction adding mass, stirring stars into new orbits, and feeding the already immense black hole at its core. By about 5 billion years ago, IC 1101 had reached something close to its present scale. Tens of trillions of stars spread across millions of light years. A black hole weighing tens of billions of suns, and something else had changed. The supply of easy mergers was running out. Most nearby galaxies had already been consumed or settled into stable orbits too distant to fall inward quickly. The long era of accumulation had come to an end. What remained was a giant that no longer needed to grow. Today, IC 1101 is still vast, still dominant, but no longer evolving in the same dramatic way. Its stars are old. Its gas reserves are low. The black hole at its center is mostly quiet, occasionally flaring when stray material wanders too close, but largely dormant. It has reached something like equilibrium. Not dead, but no longer becoming something new. A cosmic giant, slowly fading over time. And in that sense, its story is not unique. Many massive elliptical galaxies at the centers of clusters follow a similar path. But IC 1101 represents an extreme. A galaxy that existed in exactly the right conditions, at exactly the right time, to grow beyond almost anything else we have ever observed. And as we step back, we begin to see something larger. The universe itself is built hierarchically. Small structures combine to form larger ones. Atoms become stars. Stars become galaxies. Galaxies become clusters. Clusters connect into vast cosmic webs, each level building upon the one before it. IC 1101 sits near the upper limit of this process, at least for individual galaxies bound by their own gravity. There are larger patterns in the universe, filaments and walls stretching across hundreds of millions of light years. But when it comes to single, self-contained objects, this is close to the maximum scale. And that limit tells us something profound. The fact that galaxies stop growing at this size means there are constraints. Gravity, dark matter, cosmic expansion, all balancing against each other. If any of these were slightly different, the universe might look completely unlike what we see today. In that sense, IC 1101 is not just an object. It is a clue. A message about how the universe is allowed to behave. And there is something else, something quieter, something almost philosophical, about what this galaxy represents. We tend to think of ourselves as significant. Our lives, our world, our history, and in many ways, they are. But IC 1101 exists on a scale that dwarfs all human experience. 100 trillion stars, 1 billion light years away, completely indifferent to us. We are a small planet, orbiting a typical star, inside a galaxy that is itself just one among billions. And yet, from that tiny vantage point, we have discovered IC 1101. We have measured it, studied it, placed it within a timeline, stretching billions of years into the past and trillions into the future. That contrast is striking. On one side, our physical insignificance. On the other, our ability to understand. And that raises a deeper question. How did this happen at all? For us to exist, an entire chain of events had to unfold. The Big Bang had to produce matter in the right proportions. That matter had to collapse into stars and galaxies. Stars had to forge heavy elements. Planets had to form. And on at least one of those planets, chemistry had to cross a threshold, becoming something capable of replication, then evolution, then awareness. Every step depended on the ones before it. Change any part of that chain, and we would not be here, asking these questions. The conditions for intelligent observers are narrow, and the fact that we exist at all is something very close to improbable. And yet, here we are, looking outward, building telescopes, launching instruments into space, spending decades trying to understand objects we will never touch. Why? Perhaps because curiosity is not optional. It is built into us. We are pattern-seeking, question-asking, meaning-making beings. And when we encounter something like IC 1101, we cannot help but try to understand it. And then, we point our instruments at what appears to be empty space. A tiny, dark patch of sky, no larger than a grain of sand held at arm's length. And we wait. We collect light for hours, for days, and when that light is finally assembled into an image, something unexpected appears. Not darkness, but thousands of galaxies, each one a universe of stars. And this is where the story begins to shift again, because what we thought was empty turns out to be full. The universe is filled with galaxies, not a few, not thousands, but perhaps 2 trillion of them, spread across billions of light years in every direction. And I see 1101, as vast as it is just one of them. Yes, it is exceptional, larger than almost all the rest. But still, just one galaxy, in a universe overflowing with structure. And that realization shifts something, because it means that wonder is not rare. It is everywhere. We happen to focus on IC 1101. We gave it a name. We studied it. But we could have chosen almost any galaxy, and found something just as extraordinary. The universe does not hide its beauty. It offers it freely, in every direction we choose to look. And yet, there was a time when none of this was known. When William Herschel first observed this object in 1790, he did not see a galaxy. He saw a faint blur, a soft, undefined patch of light. He could not have imagined what it truly was. A structure containing 100 trillion stars. A black hole weighing tens of billions of suns. A history stretching back nearly to the beginning of time. The difference between what he saw and what we understand today is almost as vast as the distance to IC 1101 itself. And that understanding did not arrive all at once. It was built, slowly, across generations. Astronomers refining their observations, physicists uncovering the laws of nature, engineers building instruments that could see deeper into space, mathematicians developing tools to interpret what was found. Each contribution, a small step forward, until eventually we were able to look at a distant point of light and understand what it truly represents. And when you think about IC 1101, you are not just thinking about a galaxy. You are participating in that long chain of discovery, a tradition that stretches back centuries, a shared human effort to understand the universe we inhabit. This knowledge does not belong to any one person. It belongs to all of us. Anyone, anywhere, can learn about IC 1101. The universe does not reserve its secrets for the powerful, only for the curious. And there is something quietly beautiful about that. In a world often divided, the stars remain neutral. They shine the same for everyone. And the truth they reveal is the same everywhere. Now, there is one more thing worth holding on to. Not just the facts, but the feeling. Because numbers alone cannot capture what IC 1101 really represents. 100 trillion stars, millions of light years across, 1 billion years of light travel. These are measurements. But what they create is something else. A sense of scale, so vast that it gently dissolves our usual way of thinking. And that feeling, that quiet expansion of perspective, is what we call wonder. Wonder is not childish. It is not something we outgrow. It is something we return to when we encounter something too large, too deep, too real to ignore. You do not need to understand every detail to feel it. It is enough to simply recognize that this exists. That beyond everything familiar, there are structures like IC 1101, waiting, silent, immense. And perhaps the most remarkable part is not the galaxy itself, but the fact that we can know it at all. Because the atoms that make up your body were once inside stars. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it, forged in stellar cores and scattered across space, long before the Earth ever formed. You are made of star stuff, not as a metaphor, but as a literal, physical truth. The same processes lighting up IC 1101 are the processes that made you possible. So when you think about that distant galaxy, you are not separate from it. You are part of the same story. In a very real sense, this is the universe, looking back at itself, trying to understand what it is and how it came to be. IC 1101 will never know that we have discovered it. But we know, and in that knowing, something completes itself. A connection between a conscious mind and a structure a billion light years away. We are small, yes. We are brief, yes. But in the short moment we are here, we can reach across unimaginable distances and understand something so vast that it almost feels unreal. And that ability, quietly, is extraordinary. So the next time you look up at the night sky, remember, somewhere in the direction of Virgo, far beyond what your eyes can see, IC 1101 is still there. Shining, enduring, slowly evolving across billions of years. And you, standing here, are made of the same universe. The same laws, the same matter, part of the same unfolding story. And perhaps, that is the most remarkable thing of all. If this journey helped you see the universe a little differently, you can share your thoughts below. And if you'd like to keep exploring, there is always more to discover. But for now, you don't need to go any further. Just let the scale of it all settle gently into your mind. Let the questions slow down. Let the vastness become quiet. And as the universe stretches out beyond imagination, you can simply rest and drift into that quiet. Sleep well.